Hello. Today we consider our course and we start with quadrilaterals, and today we will consider some special kinds of quadrilaterals. So the first quadrilateral will be a trapezoid. What is it? A trapezoid is a quadrilateral such that its two sides are parallel and the other two sides are not parallel. So it is something like that. Well, also you can meet another definition of a trapezoid when we have two parallel sides and we don't care if the other two sides are parallel or not. But in our course we will use this definition. So let it be ABCD. ABCD. So AD is parallel to BC. And always one of these sides, AD or BC, is greater than another. So they cannot be congruent. Well, for our situation, we have that AD is greater than BC. And these two sides that are parallel are called bases of a trapezoid. So this is a base and this is a base, bases here and here. The other non-parallel sides are called legs. Legs of a trapezoid. Well, what else? As I said before, one of the base is always greater than another base. And the angle, this angle, which correspond to the greater base, are called base angles. So these angles are base angles. Also, sometimes AB is equal to CD, so we have two equal legs. And in this case, our trapezoid is called an isosceles trapezoid. So ABCD is an isosceles trapezoid. And what is the main property of an isosceles trapezoid? The main property is that base angles are equal. So if AB is equal to DC, we have that angle A and angle D are congruent. And vice versa, if we have two congruent base angles, we can say that our trapezoid is an isosceles, so its legs are congruent. What else can we say about a trapezoid? We can we can join midpoints of the legs. So something like that. So this is a midpoint, and this is also a midpoint. Maybe these two sides are non-congruent, doesn't matter. But this line, let it be EF. Sometimes it is called a median of a trapezoid, and sometimes it is called a mean line of a trapezoid. Well, we know that if we are talking about a trapezoid here, BC is parallel to AD. So if we take a sum of these two angles, consecutive angles, so their sum will be 180 degrees. So we can say that these two angles are supplementary. So angle C plus angle D is 180 degrees. Well, that's it about a trapezoid. At your practical classes, you can solve some problems in this topic. Well, let's consider another special kind of a quadrilateral is a parallelogram. A quadrilateral is a parallelogram if we have two pairs of parallel sides. So again, it is a quadrilateral. Let it be ABCD. And we have that AB is parallel to CD. As well as BC is parallel to AD. So if we use another definition of a trapezoid, that two sides are parallel and the other two sides can be parallel or not, doesn't matter. In this case, we can say that a parallelogram is a trapezoid. But again, in our course, we will suppose that parallelogram and a trapezoid, they are different quadrilaterals. So, two pairs of parallel sides. And what are the properties of a parallelogram? Well, the first property is that if we take opposite angles, they will be equal. So, angle A is congruent to angle C, so these two angles are congruent, and angle B and angle D, Angle B is equal to angle D. And if we take two consecutive angles, they will be supplementary. It means that angle A plus angle B is 180 degrees. Then about the sides of a parallelogram. Opposite sides are equal. It means that BC is equal to AD and AB is equal to CD. So opposite sides are equal. And if we take two diagonals, this and this, we can say that they bisect each other. So they meet in a point, let it be O, and BO is equal to OD, and AO is equal to OC. So diagonals bisect each other. And if we want to prove that a quadrilateral is a parallelogram, we can use these properties. So, the first way to prove it, we can use the definition. We can prove that we have two pairs of parallel sides. Or we can use this property that we have two pairs of congruent sides. Or we can use these properties that opposite angles are equal. Or we can use these properties that consecutive angles are 180 degrees together. By the way, the sum of angles in a quadrilateral is 360 degrees. So if we have that angle B plus angle A plus angle B is 180 degrees, it means that angle C plus angle D is also 180 degrees. So we can just check this fact. Or, for example, we can prove that diagonals bisect each other, and in this case, our quadrilateral will be a parallelogram again. So we can use not only the definition, but also properties of a parallelogram to prove that this is a parallelogram. And there are some special kinds of parallelograms, and the first kind is a rectangle. A rectangle is a parallelogram with equal angles. So we take parallelogram, and we say that all angles of this polygon, they are equal. And again, we know that the sum of angles is 360 degrees. It means that each angle is 90 degrees, right? Because if it is alpha, we have that for alpha is 360 degrees. From here, we can find alpha. So if we take a parallelogram and one of the angles of this parallelogram is 90 degrees, we can say that this is a rectangle. The other property of a rectangle, so properties. The first property that angle A is angle B, is angle C, and it is angle D, 90 degrees. And the second property that diagonals of a rectangle are equal. So if a parallelogram has congruent diagonals, we can say that this parallelogram is a rectangle. And don't forget that a rectangle is a parallelogram, so it has all the properties of a parallelogram. Well, the next special kind of parallelograms is a rhombus. If a rectangle is a parallelogram with congruent angles, a rhombus is a parallelogram with congruent sides. So, parallelogram. And if we know that all the sides are equal, AB is BC, CD, and AD, they are congruent, we can say that this is a rhombus. So AB is equal to BC, is equal to CD, and is equal to AD. This is the definition of a rhombus. And let's consider some properties. Well, the first property is that if we take two diagonals, they will be perpendicular bisectors of each other. It means that they bisect each other, but also they are perpendicular to each other. And the second property is that if we take a diagonal, it occurs to be a bisector of the corresponding angle. So angle BAC and DA and angle DAC, they are congruent. And again, if we have a parallelogram and we want to prove that this parallelogram is a rhombus, we can use the properties. So we can show that diagonals are perpendicular bisectors of each other. It means that this parallelogram is a rhombus. Or we can prove that a diagonal is a bisector. Again, we can use these facts to prove that our parallelogram is a rhombus. And again, don't forget that a rhombus has all the properties of parallelograms. It means that it has two pairs of parallel sides, diagonals bisect each other, consecutive angles are supplementary, and so on. And the final kind of parallelograms is a square. A square is a parallelogram with congruent angles and congruent sides. If all the angles are congruent, it means that each angle is 90 degrees. And also we have that all sides are equal. So a square is a rhombus, and a square is a rectangle. And of course, it is a parallelogram. So this polygon has all the properties of parallelograms, squares, and rectangles. Its diagonals bisect each other. Its diagonals are perpendicular bisectors of each other. Diagonals are bisectors of angles, of the corresponding angles. Diagonals of a square are equal, and so on. And if you want to show that a polygon is a square, you can show that this is a parallelogram, this is a rhombus, and this is a rectangle. And in this case, you will show that our quadrilateral is a square. Well, that's it. Any problems or questions? So everything's clear, great. So now let's consider the case when we have three or more parallel lines. Here we'll talk about midpoints and mean lines and medians, and we'll consider a concept of similarity. Previous week we considered a case when we have two parallel lines. But what if we have three or more? So this line is parallel to this line and is parallel to this line. So, for example, we have three parallel lines. Let's consider a transversal. And as you can see, three parallel lines cut off two segments on this transversal, this one and this one. And there is a property that if these two segments are congruent, it means that if we take any other transversal, I will mark it with another color, these two segments will also be congruent. Maybe the length of this segment and this segment, so they will be different, doesn't matter. For us, it is important that the lengths of these two segments are equal. So let's write it down. If parallel lines cut off congruent segments on one transversal the cut off congruent segments on any other transversal. Maybe we have more than 3 parallel lines. It means that we have more than 2 segments, 3 or maybe more. And if all the segments here are congruent, it means that all the segments here are also congruent. Then, if we consider a triangle ABC, and we take a midpoint of AB here, let it be C1. Also, we take a midpoint here, A1. This segment, C1A1, is called mean line of a triangle, and it is parallel to the third side, AC, and its length is 1/2 on the length of AC. So A1, C1, it is a mean line. We know that C1A1 is parallel to CA, and C1A1 is 1/2 of CA. And vice versa, if we take a triangle ABC, and we take a midpoint of, for example, AB here, C1, and we draw a line which is parallel to AC. This line intersects BC at a midpoint of BC. So if it is a midpoint, it is also a midpoint. So if AC1 is C1B, and C1, let it be A1, and C1A1 is parallel to CA, it means that BA1 is A1C. So if a line passes through a midpoint of one side and is parallel to the second side, it passes through a midpoint of the third side. More than that, if we have not a midpoint, but another situation, if we have a triangle ABC, and we take a point here and a point here, and it occurs that these two line segments are in proportional. It means that, no, let it be again C1, C2. If BC1 over C1A is equal to BA1 over A1C, so these four line segments are in proportion. It means that C1A1 is parallel to AC. And vice versa, if we take a triangle ABC and we take a line which is parallel to one side, it means that this parallel line will divide two other sides proportionally. So if it intersects AB at C1 and intersects BC at A1, it means that BC1 over BA is BA1 over BC. So again, we have that A1, C1 is parallel to AC. Then we can make a conclusion that BC1 over C1A, no, it's better true. This is also true, but we'll write, no, we'll write C1A. So C1A is BA1 over A1C. Then, if we take a trapezoid and we take a mean line of a trapezoid, so this is our trapezoid ABCD, we take mean line, so this is a midpoint of AB, let it be E, and this is a midpoint of CD, let it be F. So in this case, EF is parallel to BC and to AD. And more than that, we know the length of EF. It is 1/2 of the sum of bases. So EF is a mean line. It means that EF is parallel to BC and BC is parallel to AD. And EF, the length of this line segment, is 1/2 of a sum of lengths of the bases, BC plus AD. And vice versa, if we take a midpoint of one leg of this trapezoid, ABCD, let's take a midpoint here, and if we draw a line which is parallel to the bases, we know that this point will be a midpoint of CD. So if BD is equal to DA, if DE is parallel to BC, or we can write that DE is parallel to AD, it means that CE is equal to ED. Next, if we have 3 or more parallel lines and 2 transversals. So we have 3 parallel lines and 2 transversals. And we can say that parallel lines divide transversals, any 2 transversals, proportionally. So if it is A1, A2, A3, here we have B1, B2, B3. We can say that A1, A2 over B1, B2 is A2, A3 over B2, B3, and so on, if we have, for example, 4 or more parallel lines. Proportional. And now let's talk about medians and bisectors in a triangle. So if we have a triangle ABC and we consider its medians A1, B1, and CC1, it occurs that all three medians meet in one point. And more than that, this point is 2/3 of the distance from a vertex to the midpoint of the opposite side. If this point is O, for example, we can say that CO is 2/3 times CC1, as well as BO is 2/3 BB1 and AO is 2/3 AA1. By the way, all altitudes and all bisectors of a triangle also meet at one point. And if we consider a bisector, ABC, and this is BD, and BD is the bisector of a triangle ABC. We can say that this bisector divides AC proportionally to the adjacent sides. It means that BD is a bisector. So AB over BC is AD over CD. And again, if we take all three bisectors in a triangle, they meet at one point. What else? If we consider a triangle, a right triangle, so if one of the angles of a triangle is right, so ABC, and we draw a median, we draw it from this right angle, AA1. It occurs that this median is equal to the half of a hypotenuse, BC. So we can write that BA1 is equal to A1C and is equal to A1A. So A1A is a median. So AA1 is BA1 and it is A1C. Okay, what else? So I guess now we can talk about similar triangles. And not only about triangles, but polygons, quadrilaterals, doesn't matter. We say that two figures are similar if they have different, maybe they have different size, but they have the same shape. It means that if we're talking about a triangle, it's the sides of one triangle are proportional to the sides, to the corresponding sides of the another triangles, and the corresponding angles are equal. So, similarity. So this is A, B, C, and this is A1, B1, C1. So they have different sizes, but they have the same shape. And we say that triangle ABC is similar, we use this symbol, is similar to triangle A1, B1, C1 if angle 1 and angle A1 are congruent, as well as B and B1, C and C1. And also we need AB over A1, B1 is equal to AC over A1, C1. And this is BC over B1, C1. So all the sides, they are proportional to each other, and the angles are equal. So again, they have the same shape, but different sizes. But usually it is very complicated, I mean technically complicated, to show that two triangles have three congruent angles and their sides are in proportion. Right, so we have three cases, we have three principles of a similarity of a triangle. So the first principle, ABC, A1, B1, C1. If we have two pairs of equal angles. So if this angle and this angle, they are congruent, and if B1 and B are also congruent, we can say that these two triangles are similar. It means that we have proved that their sides are in proportion. So if angle A is angle A1 and angle B is angle B1, it means triangle ABC and A1, B1, C1, they are similar. The second case, again ABC and A1, B1, C1. And now we have just one pair of congruent angles, this angle and this angle, and we have one pair of proportional sides. So we have B1 and B, these two angles are congruent, and also AB over BC is A1, B1 over B1, C1. So if two angles are congruent and two sides, two corresponding sides are in proportion, we can say that two triangles are similar. And the final case, when we have three pair of proportional sides. So again, ABC and A1, B1, C1. And we have that AB over A1, B1 is BC over B1, C1, and it is AC over A1, C1. In this case, we can say that ABC and A1, B1, C1 are similar. It means that their angles are congruent. So now let's take a break for 5 minutes. And now let's try to apply a similarity of triangles to right-angled triangles. So, if we consider triangle ABC And one of the angles is a right angle, angle A, for example. And if we take an altitude, A1, what can we say here? If this angle is alpha, angle C, it means that this angle is 19 degrees minus alpha, right? Because we know that the sum of angles inside a triangle is 180 degrees, and we have one right angle and one angle is alpha. So this is 19 degrees minus alpha. But it means that this angle, BAA1, here is also alpha, right? Because this is 90 degrees minus 90 degrees minus alpha, right? So what do we have here? We have that triangle ABA1. One angle is right angle and one angle is alpha. Is similar to triangle CAA1. Right? Because A is equal to C. I mean, angle A and angle C, they are congruent. B and A are congruent, and A1 they are congruent because they are two right angles. So we use the first case of similarity. And now we can use the fact that these two triangles are similar. It means that their sides are in proportion. So we can write that AB over CA is BA1 over BA1 over A1A, for example. And it is AA1 over CA1. And we can use this part from here. We have that AA1 squared is BA1 times A1C. Well, AA1 is an altitude, so the length, the squared length of an altitude is the product of line segments, on which this altitude divides the hypotenuse. Also, we can use this concept of similarity to prove many other properties of right-angled triangles, and not only in right-angled triangles. Well, and the final topic for today is a circle. What is a circle? A circle is all points which are equidistant from a point. So we can choose a point here on a plane, let it be O, and then we take all points which are equidistant from this point. And this is a circle. And this point O, it is here, right? Or it's better to write it here. This point O is called a center of a circle. And this distance around the circle is called a circumference. If we take a point here on a circle and we join this point with the center of a circle, we'll get a line segment called radius. And sometimes we say radius when we mean this line segment. Sometimes when we say radius, we mean the length of this line segment. So we can say the length of radius, or it's better to say just a radius. If we take 2 points on a circle, this line segment, and join them, this line segment is called a chord. And if a chord passes through the center of a circle, it is called a diameter. And for example, here you can see an angle formed by two radius. Let it be A1 and A2. OA1 is a radius and OA2 is also a radius. And this angle A1, OA2 is called a central angle. This angle. So we can say that a central angle is an angle whose vertex is the center of a circle. What else? If we take a continuous part of the circle, this continuous part is called an arc. For example, this A1A here is an arc of a circle. And if we divide a circle into two equal parts, we will have two equal arcs. We say that we have two semicircles. And also we can introduce such concepts as minor circle, minor arc, and major arc. It means minor arc is an arc which is less than a semicircle, and a major arc is an arc which is greater than a semicircle. And if we take 3 points on a circle, for example, here, here, and here, we can join them, and also we have an angle. And this angle is called an inscribed angle. And if we are talking about inscribed angles, we can say that to each inscribed angle we have one and only one corresponding arc. Right? For example, for this red inscribed angle, we have this red arc. And we say that this angle intercepts an arc. An arc, this B1B, for example. B1B. Then, if we have two circles, we can have different situations. The first situation is when they have the same center. So this is O, and we have one small circle and one large circle. And in this case, we say that we have two concentric circles. Before we go to the other kinds of two circles on a plane, we need to consider such concept as a tangent line. So if we have a circle and we have a line which has one and only one point, one and only one common point with this circle, we say that this line is a tangent line. So we can say that a tangent line touches our circle. And if we have a line which has two common points with the circle, this line is called a secant. Well, back to two circles. The first situation is when they are concentric, but also they can touch each other. And sometimes they touch externally, sometimes they touch internally. What does it mean? The first situation is when we have one circle here and one circle here. Yeah? They have one and only one common point. So in this case, they touch internally. And what can we say here? We can say that if we take a radius of this large circle, and we join this, the center of the large circle with the center of a small circle, and then when we produce this line until it passes through a point on a small circle and on a large circle, this line will be a diameter of a small circle. So we can say that this point, B, for example, B is the point at which they touch each other. This is O1, and this is the center of a large circle, and this is O2, the center of a small circle. We can say that these 3 points, O1, O2, and B, they lie on the same line. And also, the distance between the centers, this D, for example, we can say that this D is O1B minus O2B, that is R, capital R, minus small r, where capital R is the radius of a large circle and small r is the radius of a small circle. So this is R, small r, this is capital R. So the distance between these centers is the difference between their radius. And if we consider another situation when they touch each other externally, here and here, this is O1 and O2, and again if we join O2, and again if we join two centers, we can be sure that this line passes through this point when they touch each other, point B, for example. And if here we want to find the distance between the centers of these two circles, it will be the sum of their radii. So O1, O2 is R. This is the radius of this circle, plus R, this is the radius of this circle. Maybe these two circles are congruent. It means that their radius are equal, but maybe not. And if they are not congruent, they have two common tangent lines. And we can be sure that, these two tangent lines will intersect somewhere. If they are congruent, I mean these two circles are congruent, it means that they have the same radius. These two tangent lines will be parallel, so they will never meet. And also in this case, they have another common tangent line here. If we are talking about this situation, they also have a tangent line, a common tangent line passing through B here. Then sometimes we have a situation of overlapping circles. What does it mean? It means that we have one circle, another circle, and they overlap like this. This is the center of the first circle. This is the center of the second circle. And as a situation, they have the common chord, AB, for example. AB. Well, if these two circles are not congruent, if they have different radii, it means that they have two common tangent lines, and these two tangent lines will intersect somewhere outside the circles. If they are congruent, it means that they again have two tangent lines, but these two tangent lines will be parallel. And the last case of two circles is when they are outside each other. One is here and one is here. Here we can say that they have two pairs of common tangent lines. The first pair is, well, how to say, is inside maybe, here. The first and the second. And they always intersect. And also we have another pair of tangent lines, here and here. And these two tangent lines, they intersect if we have non-congruent circles, if their radii are different. And if we have two congruent circles, these orange tangent lines are parallel, so they will never meet. So for five kinds of two circles: concentric, touch inside, outside, overlapping, and outside each other. Also, we have a lot of properties of secants, chords, arcs, and so on. And let's consider some of them. Again, we just formulate all the properties. We will not prove them, but you can use them at your practical classes to solve your problems. So, a circle. And let's consider an inscribed angle here. And if we consider the corresponding central angle here, O, let it be beta, and let it be alpha. We know that beta is to alpha. So the central angle is two inscribed angles. What else? If we consider two, and if we consider a central angle, we can say that we have a corresponding chord, and we can measure chords with central angles. So if we want to say that this chord is, I don't know, gamma degrees, we can measure this central angle and say that this chord is beta degrees in our case. So if inside the circle we have two chords, this one and this one, and these two chords are equal. So this is the length of the first chord is D1 and the length of the second chord is D2. And we know that D1 is equal to D2. It means that the corresponding arcs, this one and this one, are equal. And vice versa, if we have two equal arcs, we can say that the corresponding chords are also equal. And again, if we talk about arcs, we can talk about central angles. So if we have two equal arcs, we can say that we have two equal central angles, as well as two equal inscribed angles, because inscribed angle is 1/2 of a central angle. And usually we use this property when we want to show that two inscribed angles having the same arc are equal. So this angle is equal to this angle, right? Because they intercept the same arc on a circle. Well, next, with chords, if we have two equal chords, we can say that they are equally distant from the center. So the distance to the center from the first chord and this distance and this, they are equal. So two congruent chords are equally distant from the center. And vice versa, if we have two chords and we know that they are equally distant from the center, we can say that they are congruent. And if we take an angle, inscribed angle, and the corresponding arc is a semicircle, so this is a diameter, and we consider this inscribed angle, we can be sure that this inscribed angle is a right angle. What else about circles? Here we can consider so-called inscribed polygons and circumscribed polygons. What are they? So if we have a circle and we have a polygon, and all the vertices of this polygon lie on this circle, A1, A2, A3, A4. In our case, this is a quadrilateral, but it can have, for example, 4 or 5 or more sides. So this quadrilateral, A1, A3, A4, A1, A2, A3, A4, we say that this is inscribed in a circle. So this is inscribed polygon, inscribed quadrilateral. And with respect to this quadrilateral, we can say that the circle is circumscribed. circumscribed circle. Or another situation when we have a circle and we take a polygon such that its sides are tangent to this circle, something like that. So this is A1, A2, A3, A4, A5. Well, we say that this polygon is circumscribed with respect to the circle, and the circle is inscribed. And now let's consider some properties of inscribed quadrilaterals and circumscribed quadrilaterals. Okay, I will use this whiteboard. So we have a circle. And we have a quadrilateral. And we know that this quadrilateral is inscribed in this circle. A1, A2, A3, A4. We can say that consecutive angles, this and this, now we can say that opposite angles, this and this, they are 180 together. And again, we know the sum of the circles inside a polygon, a quadrilateral, this is 360. So we can say that A1 plus A3 are also 180. And vice versa, if we have a quadrilateral, and we know that the sum of opposite angles is 180, we can say that we can inscribe this polygon into a circle. And vice versa, if we have a circle inscribed in a quadrilateral, we can say A1, A2, A3, A4. We can say that a sum of opposite sides are equal. It means that A1, A2 plus A3, A4 is equal to A2, A3 plus A1, A4. And vice versa, if we have a quadrilateral and we know that the sums of opposite sides are equal, we can say that we can circumscribe this polygon around a circle. Well, we have 10 minutes left, and now let's talk about different angles in a circle. The first thing is if we have a tangent line to a circle, and we have a radius of a circle, we know that these two lines, for example, AB, yeah, here is A, here is B, this is C, we know that they are perpendicular. So AB tangent line CO radius. So we have AB is perpendicular to CO. So a tangent line is always perpendicular to the radius drawn from these points when they touch. And vice versa, if we have a tangent line, so AB tangent line, and we have a line, and we know that this line is perpendicular to this tangent line, and this line passes through this point when these tangent lines touches our circle. We know that this line CO passes through the center of a circle, so CO is a radius. And the third property here is that we have a tangent, if we have a radius, and we have a line, and about this line we know that it passes through a point on a circle, and we know that this line is perpendicular to this radius. We can say that this line is a tangent line. So if AB is perpendicular to CO, C lies on AB, and CO is a radius, it means that AB is a tangent line. Well, okay, and about some other angles. If we have a circle, if we have a tangent line, and if we have a chord, and one of the ends of this chord is this point when they touch, and if we consider this angle, alpha, this angle alpha between a tangent line and a chord, this angle will be equal to this inscribed angle. Or it's better to say that this angle is half of the central angle corresponding to this chord. Also, if we have two intersecting chords inside a circle, this is alpha, we can say that an angle between these two chords is a half of a sum of these two arcs. This arc is beta, for example, and this arc is gamma. So alpha is beta plus gamma over 2. So the angle between two chords is a half of sum of the angles measured by two intercepted arcs. If we have two secants and we intersect outside our circle, we can find this angle alpha. Alpha is a half of sum of two arcs intercepting by these two secants. So this and this, not a sum, a difference. So we can say that alpha is, let it be beta, and let this arc be gamma, is beta minus gamma over 2. And if we have one secant and one tangent line to a circle, this is a tangent line, and this is a secant, and they intersect at a point outside the circle, we can find this angle alpha. And again, this angle is half of difference between two intercepted arcs. This arc and this. This is beta, this is gamma. So alpha is beta minus gamma over 2. And finally, if we have two tangent lines, and if they intersect outside the circle, alpha, we can find this angle. This is a half of a difference between two arcs. This arc, beta, and this arc, gamma. So alpha is beta minus gamma over 2. By the way, if we consider this situation when we have two tangent lines and they intersect at a point outside the circle, and if we take this point and we join it with the center of the circle, let it be A1, A2, A, and O, for example. It occurs that OA is a bisector of angle A1, A, A2. So these two angles will be equal. Well, we have 3 minutes left. I don't want to talk about different line segments in a circle because we have not so much time. So let me stop here and we'll continue next week if you don't have any questions. So thank you for the class and goodbye. See you next week.